learning paper was covered on Sports Illustrated. So let me jump into the meat of the talk. I hope I've convinced you that behavior data is very interesting. Behavior modeling is very interesting. Let me jump into the meat of the talk. So the meat of this talk is about how do we think about where programs and neurosymbolic reasoning fits into the machine learning landscape. And there, as a machine learning person, to a first order approximation, I would decompose, I would dichotomize machine learning into data versus priors. So on the prior side, we have things like the raw data, of course, environmental rewards or data augmentation. And on the data side, we have things like, on the prior side, we have things like inductive biases, everything from like convolutions as a form of inductive bias to neurosymbolic function classes as an inductive bias to controllers like PID controllers and so on and so forth. And I would argue to a first order approximation that the bulk of the talks we've seen in this kickoff meeting have been about how do we put neurosymbolic modalities into the prior, into the function class. There have been some talks on programmatic supervision or how do you use programs to generate new data, but that's going to be, but not a lot. And that's going to be the focus of this talk. How do we use programs and neurosymbolic reasoning to generate new forms of data augmentation or supervision augmentation to do better learning? And so let me just start by grounding it in content generation. That's going to be the bulk of this talk. And so let me just start with a motivating application. So let's say we want to do style calibrated generation. So the goal is controllable generation of behaviors that are calibrated to different styles. For instance, suppose we want to generate behavior from the starting point, the black circle, this is of, let's say, NBA movements of NBA players, from that circle to the basket. And we want to generate it according to two different styles. This is a very simple example, a more aggressive style and a more circumspect or passive style. So in some sense, we want this deep learning policy that takes as input a state, it takes as input a style, and then outputs a sequence of actions that realizes or generates that style that achieves that action. So of course, there are many possible styles. If you just look at the expert demonstrations, which in this case come from real NBA games, we can see that there are many different styles in these demonstrations, ranging from speed to destination or combinations of different styles simultaneously. And so how do we build learning algorithms that can be calibrated to generate behavior across all these different styles? And so here are the two key challenges. First of all, when I say these, when I talk about styles, I think the first thing one might think of in terms of actually obtaining these styles is, well, we should just annotate, right? Let's annotate these replays to have these styles. And traditionally, that's actually what's been done. Of course, that is very expensive, and they typically often need to even be done by experts and not just by lay people, such as Mechanical Turk workers. The second challenge is that as you want to calibrate to many styles simultaneously, the joint style space scales combinatorially with respect to the number of styles. And so our solution is to use programmatically generated supervision, where an expert simply writes a labeling function for a style, and that can be used to annotate and provide weak supervision for the entire data set. And then through that, we come up with a new style consistency learning objective that can exploit the supervision to do learning more reliably. And so labeling functions can be very simple, right? So here's a simple labeling function where we simply ask, does the termination of this trajectory terminate close or far from the basket? And this is a very simple example. And you could write down a function like this lambda function you see in this example that just measures whether the termination of the trajectory is close or far from the basket. The advantages are that it's fast to compute. You just write this function once and you just run on your entire data set. It compactly encodes domain knowledge because the function in principle should be written by experts. And oftentimes these things are readily available. If you talk to sports analysts, which are basically applied statisticians that have been looking at these trajectory data for years, they've been writing these types of scripts to filter and manipulate and apply metadata to these trajectories for years. So in many cases, these types of labeling functions are actually readily available. I should also mention that we took inspiration from this paper that I'm linking in the bottom called Data Programming by Alex Ratner and Chris Ray, where they applied this to non-trajectory data, and we have sort of extended this idea to trajectory data. And so now that we have a handle on how to actually get these style labels, we can ask the question, okay, what is a good learning objective? And so in other words, if I want to generate style calibrated behavior, what is a good measurement of whether or not the generated behavior is good? Of course, on the one hand, it should be realistic, which is a fairly standard imitation learning objective. On the other hand, the generated behavior should not only be realistic, but also be consistent with the input style. So if we ask the model to generate behavior that, let's say, terminates in that band between the two blue lines, then the generated behavior should actually do that. And one way to do this is we can actually use our labeling function to check for the termination condition in this case, and check if the termination condition satisfies the labeling function. In other words, we want to directly optimize for a notion of style consistency. And this can be extended to multiple styles. The left-hand side is standard imitation learning. I don't want to talk about it. The right-hand side is basically saying that the trajectories generated by our learned policy should be consistent with the imposed styles, where the lambda function is written by the expert. And you can see papers for the actual algorithm that we use to actually optimize for this objective. I just want to show you some results of our learned model. So this is optimizing for two styles simultaneously: slow speed, medium speed, fast speed, and terminating at a medium distance from the basket. So let's look at the left. This is slow speed. Let's look at the middle column at medium speed. And then let's look at the right at fast speed. You can play around this yourself. I won't give you a live demo in the interest of time, but if you go to our very creatively named basketball-ai.com website, you can play around with this yourself. We've deployed this just for your personal consumption. The other thing you can do is you can apply similar approaches to hierarchical modeling, where you can model not only the step-by-step actions, but you can also model sort of sub-goals. And so here you're seeing a visualization where we're showing the macro goals or sub-goals along with the step-by-step actions. Here's just another visualization. We can use these things to see that these models capture interesting multimodal distributions of behaviors. So if you roll out from the same initial conditions, you get, in this case, a distinct multimodal set of outcomes. You can even ground the sub-goals. So here in the right plot, we force the sub-goals to be at two different locations. And you see that the low-level planner is able to sort of generate low-level actions that obey these sub-goals. So if you're interested in the details, you can check out these papers. So I want to switch gears a little bit and spend 1 minute on cataloging and detection. So we spent the bulk of this talk on generation. So cataloging and detection is typically done via supervised learning. And most of this work is motivated by our collaborations with behavioral neuroscientists here at Caltech. And so one of the biggest bottlenecks in behavior modeling and behavior cataloging is annotation. So typically, a biology PhD student would spend hours annotating the behaviors frame by frame in order to do their subsequent analysis that connects activities in the brain to phenotypes like behavior. And this is extremely expensive and must be done by experts. And so this is a huge bottleneck. And so our goal is to figure out how to learn annotation efficient representations to ease the burden on the experts' annotation. And so this is ongoing work done by PhD student Jennifer Sun at Caltech. And the details of this slide doesn't really matter. What matters is the red words and the purple words. So essentially, we're taking the same broad design principles from the content generation. We basically say, well, we're going to have all these auxiliary decoder tasks to decode, in this case, let's say style consistent behaviors, as programmatic weak supervision for decoder tasks. And these decoder tasks will help us learn a more efficient, semantically efficient representation when we encode the trajectory behaviors. And therefore, these encodings will then be used for downstream supervised classification, ideally using far fewer annotations than the previous work. So that's the basic idea. And so here's some preliminary results. This work is in preparation. We're hoping to submit it to CVPR in about a month and a half. And so here in this preliminary result, we see that these encodings trained using these augmented programmatic supervision, these representations can be much more data efficient in the downstream supervised learning task. And so here you see that at 10% of the full annotation data, our approach achieves comparable accuracy with the prior work at 100% of the annotation data. In other words, just by having the expert write some labeling functions about key attributes that they think should be encoded in this representation and having that be a decoder task, we can lead to a 10x efficiency in annotation effort. The next step, of course, is discovery, which is an unsupervised learning task where just from this trajectory data, we can discover new things. Like, suppose we didn't know that a lunge was a behavioral attribute that we want to model. How do we automatically discover these types of labels from data rather than having the expert handcraft them manually? And we haven't done much in this space yet, but that's our next step. So stay tuned. And just to summarize, this talk is about how do we use experts to write programs to create supervision that can be useful in various contexts. So I call these, what people can call these labeling functions. They lead to programmatic supervision. And the two applications that I've talked about is controllable generation and efficient representations for downstream supervised learning. Finally, I'd like to thank the collaborators, especially the people in the top row who did the bulk of the work, especially Eric and Jennifer on the left, top left. And finally, if you're interested in the references that have been published, that were referenced in this talk, they're available here. And if the slide deck will be made available on the workshop website, I'm happy to make these available broadly. Thank you for your attention.
Can you hear me? All right, sounds great. And you can see my slides? Okay, great. So today I am going to talk about the work that we have going on, or that we're exploring and thinking about on the computer systems push inside of the expedition. In particular, one motivating trend here for computer systems, and I'm not going to belabor this point too much, is that which is going on with Moore's law. The fact that Moore's law is coming to an end. And what I mean by that is this era of exponential improvements in single thread performance, in a single processor with a single core that we can execute on our single threaded application. That's been coming to an end. It's been coming in for some time. And although we've been seeing still significant increases in the number of transistors that are available in underlying processors, the way that's been exposed to us is through more cores, more parallelism. And so I'm not going to get into too much around details about parallel computing models, but instead, think about what Moore's law is telling us about how perhaps we're going to get better single thread performance coming to the future. And in particular, if you look at the computer architecture community, there are a couple of directions that they've been pursuing and thinking about that I'll characterize as either heterogeneous or statistical computing. In the heterogeneous setting, researchers have been considering ways of building domain or application-specific hardware accelerators that allow you to just map specific applications or parts of your application down to an accelerator. On the other side, statistical, and what they're doing here is actually exploiting new computing substrates that just fundamentally return different styles of results. And so just to concretize that a bit more, heterogeneous computing, if I take my TensorFlow or PyTorch program, I have this, this eternal question: do I run this on the CPU, GPU, the TPU? What is the particular deployment context that I'm working in? How do I make this decision? And the heterogeneous computing model, sort of in its full fruition, takes this perspective of trying to figure out how to decompose perhaps very small parts of your application to run on a wide variety of general purpose hardware components, such as a CPU, down to a very highly tuned application specific component, such as a TPU, which has been specifically designed for these machine learning workloads. Right? Now, on the statistical computing side, the way I characterize this is, quite simply with a couple cartoons. Where on the top, we have our traditional computing, where I take an input, I pass it into my program and execute it, quite normally, and I get a single input on the outside, assuming I'm working in deterministic context. But in these new statistical computing models, we're thinking about, or what we're seeing are models like quantum or analog or stochastic or approximate computing, where what happens is you get an input, and as an output, what you get is a distribution over outputs. And so there are these fundamental questions about, well, what's the probability that I get the correct result if I execute my computation on this type of alternative substrate? So that gives us to what I'd say are some of the emerging trends that are going on in computer systems and how we think these will evolve, where what we need to be able to do now is fairly precisely characterize, say, the performance of a given application on a given piece of hardware, but also now even its behavior. What does it actually produce on some given hardware that's been given to me? And so what I'd say is, the challenge that we're seeing now is that on the left, what we'd like to do is go from a program, a hardware specification, and then both a performance model and behavior model, and then be able to learn how to map this to, well, this sea of potential hardware components that we're going to see down at the bottom. And so this is one of the major challenges that I'd say that we're seeing coming up in the computer systems area in the future, which is, how do you effectively navigate mapping software in an automated, scalable way to just the sea of different systems that may be showing up, so that we can still continue to execute the applications that we so care about. So in this talk, what I'm going to do is I'm going to talk about our work on learning neurosymbolic performance models, so just the performance model of this work, of this diagram. And in particular, I'm going to talk about some work that we have coming up in micro quite soon, called DiffTune. With the goal is that we want to use synthesis-like techniques to synthesize parameters for programmatic performance models. And what we're going to do here is we're going to use a differentiable surrogate optimization technique. And so together at the end, what we get is a interpretable program where we've learned its parameters via deep learning. And of course, I'm not going to get into this into any much detail, but beneath all of this, of all these systems that we're building, there are very interesting questions about what do these neurosymbolic programs mean, right? These are now real valued probabilistic differentiable programs, and the programming languages community and aspects of the systems community haven't really fully explored, I'd say, a lot of the semantic concerns. And so that is one place that we do, as a group, actually spends quite some time thinking about what are the semantic challenges of these systems. So anyway, so on to performance modeling. So what is the performance modeling challenge? So the one I want to talk to you about is this, where I want to talk about predicting the time it takes for a basic block to execute on some piece of hardware. And this is critical. This is critical to the grand emerging challenge that I talked about, but it's critical to a wide variety of different performance sensitive tasks, where the idea, at least in the way that I want to explain it, is I want to take some assembly code, a linear sequence of assembly code instructions, and then predict how many cycles it actually takes for this thing to execute. Specifically in this steady state, if I had an infinite number of these things looped end to end. And so we're going to call that throughput. Now, so the reason why this is a hard problem is because one, your modern processor is actually quite complicated. This is a cartoon diagram of Intel Skylake architecture, and it's quite detailed in that instructions come in through this front end that we see at the top left, transfer through many of these various pipelines, being translated down to a lower level micro-op representation, then being scheduled, executed on specific execution units, and then, of course, retired, and as well as dealt with various memory concerns. And so this is, if in principle you want to build a highly precise performance model, you are thinking of modeling many of the aspects of this cartoon, and each of these have their own individual logic and parameters associated with them. And what makes this even more so difficult is that this is the real picture that we actually have of this architecture, where we have some hints, but really the best access that we have is via measurements, where we can run code on the underlying processor to get results, right? Now to these hints, I'll talk a bit about these hints, and it's hard. Intel does provide us some hints, right? So it provides us a wide variety of textually written documentation, so thousands and thousands of pages in the Intel manual. I've got instruction specifications, optimizations that the processors do implement, parameters, instruction throughput. So it's a lot of it's there, and you see a lot of tables. But these are all, as Intel will admit, approximations, where they actually say, if you go and look through this material, all tables in this appendix are estimates. Actual performance can vary from somewhat faster to significantly faster than what's reported, right? And the reason why is because this is just a very complicated machine. And it's very hard to precisely pin down the value of some single parameter that they can give you as a useful abstraction, or a precise abstraction in all cases, right? And in fact, if you were to sit down, or you're a performance engineer, if you're working in the LLVM compiler infrastructure, what you're going to do is you're just going to abstract away a lot of these details and build a performance model that has a few simpler components that you'll go ahead and model with parameters. And then, so what you get is a very simplified setting where you pass in a basic block into your abstract model, and then you get a number. All right. Now, to explain this in more detail, just to see how really challenging this is, I'd like to go through an example here. The example is, how many cycles does it take to compute 100 iterations of this following instruction? Now, of course, I do not at all expect you to know what this instruction means, but we can go and dig through the Intel manual and figure out what this means, right? We can find the appropriate page, and it tells us this is actually a bitwise XOR of some vector registers. And so we can rewrite that to be something that's more interpretable, which says I've got some register R1, and I'm going to set its value to be R1 XOR R1. Now, what I can do is also go flip through other parts of the Intel manual and now get some of the base parameters that Intel offers to us. Where it's going to say for this particular instruction, here's the latency. So it takes 1 cycle to compute this instruction. And then here's the throughput. And the way to model this number is what it says is if I have 3 instances, independent instances of this instruction, I can complete all 3 in a single cycle. And so that's the way to think about it. All right. Now, so what is this, to the top line question? In principle, you'd hope this was enough information to recover it. And when I go through this talk and I give it in person, one of the first things that comes up is this should take 100 cycles. And this is, if you look in LLVM's implementations, it does actually say 100 cycles. And the reason why is because it says, well, this instruction instance assigns to R1, but it also depends on R1. So there's this dependence. And of course, I can't finish computing one instruction until I've finished computing one of its prior dependencies, right? So you get 100. There's 100 instances of this instruction, and each take 1 cycle. Makes sense. Now, if you spend some time, or if you're up to speed on your bit twiddling hacks, you know that R1 XOR XOR, or any value XORed with itself, is actually going to give you 0. And so actually, instead, you can rewrite this code to look a little bit more like this, where it just says R1 is equal to 0. And sure enough, if you go clawing through Intel's manuals, you'll find that it actually implements this optimization. So you have to find a whole nother part of the manual to go hunt this down. But you'll see our instruction in there, and it says, yes, these actually have no execution latency. And therefore, we can actually change this so that all 3 of these execute in the same cycle, as we'd expect. So 3 based on our throughput number. Now, of course, you would hope. This is making more sense. We're getting closer to the real number. But if you measure this, what you actually see is you get the number 25. And the reason why is because once you've made this change, now you're actually getting bottlenecked by an entirely other part of the processor, which has a different specification where it can actually process 4 of these in the same cycle, right? So starting from our very reasonable understanding from the get-go, we can see that the actual measured performance goes through many, many different perturbations and optimizations before you actually get to the result that we care about. And so what it means is that in practice is if you are building these types of models, what happens is this: you have your abstract model at the top, you have your actual processor at the bottom, you take some set of programs that you'd like to characterize and actually use to characterize or test your model. You passed one through the top, you pass them through the top, pass them through the bottom, you take the difference to see where your model is inaccurate, and then you refine. Now, if you look at this, you can see what we've got is sort of your standard just training loop in a machine learning algorithm, except you've got a human here in the loop. Right, so some work that we did a while ago is what we did is we went and we took this observation and said, why don't we just replace this with a neural network and try to use gradient descent and see if we can actually just learn performance models raw out of x86 basic blocks. And the answer was actually, it's a astounding success. Yes, we can do this. And essentially, with our models, we can halve the error of both LLVMs and Intel's own proprietary tools that we don't have source code access to. So we can cut those error rates in half. And the way that we did this is, there's some minor details to the network that we use, but I'm not going to delve into that too much. But what we really did is, a lot of the work went into the data set measurement and collection process here, finding 1.4 million basic blocks and measuring these according to a fairly thorough assessment of the basic invariance that we want to be true of timed measurements for this system. And so, like I said, I'm not going to get into too much of the details here, but the major distinction here that we've seen is that with our IFML model, there's no featureization. So this is all done with basically just learning representations, representation-based learning, where we're taking raw x86 text and actually able to produce these predictions. And so this is a nice point of distinction versus much of the previous work that's ever been in this space where people do this hand featureization. So the result is, if we go back and look at our example, we get the following, right? LLVM was 100, Intel's IACA came in at 25, and IFML, our learned model, comes in quite close, right down here at 26.8, all right? So that was nice. So we went from this, an abstract model that you have to write by hand, to a much more precise neural model. But it would be nice, and certainly given the charter of this expedition, but to explore, what is a neurosymbolic model, right? And in particular, with IFML, if we wanted to give a prediction, let's say to a performance engineer to say, this is how long your code takes, go off and fix it, they don't really have a working explanation on what to change, right? And so instead, what we've been exploring are these neurosymbolic models. And in particular, what we did is, if we go back to the slide that we had before, we took a look back over to IFML and said, well, could we actually go ahead or to not IFML, but to LLVM, we said, could we find ways to learn LLVM's parameters, right? It's this large, discrete simulator that actually gives you a trace and explanation for why it gave a prediction. Could we actually figure out a way of actually learning those parameters? And so the answer is yes. And so this is some work that we have just coming out in Micro next week, where what we did is as follows. So LLVM MCA, this is the simulation tool that we were talking about in these previous slides that's inside LLVM's source base. So LLVM, this is a very highly used compiler infrastructure, if I haven't said it already, that's used in many, many devices. And so this LLVM MCA model is used to validate many aspects of some of the back-end optimizations that are in LLVM's implementation. And so this program that we're looking at, it's got 10,000 lines of code and actually 11,000 integer parameters, integer value parameters that we'd like to learn. And I'm not going to explain this in detail, but it has a fairly precise simulation, or more precise than the cartoon that even the little abstract cartoon I showed before, where through each one of these stages there's a whole set of parameters. So instructions come in, they're dispatched, they sit in a reorder buffer until their dependencies are satisfied. They then get scheduled on execution units. And those execution units, everything in this pipeline has a whole set of parameters associated with it. Fully 11,000 in total when we actually look at the instructions that we have. Now, to learn this, if we think about using some sort of heuristic search, this space is just too large, and we validated it versus some baselines, some random search baselines, and even bandit-based search baselines. And instead, we decided to go a different approach, where what we did is use differentiable surrogate optimization. So the idea of surrogate optimization is it's an old technique where what I do is I have a model that I'd like to optimize, and I'm going to replace it with a surrogate that is easier to optimize. And so here, what we do is, this is a characterization of the optimization problem we would like to solve, where F, think of this as our simulator, this 10,000 line of code simulator that we have. And what we want to do is find a minimal set of parameters, theta, that essentially minimize its loss, given a data set D and some loss function that we have available to us. And what we do is we translate this optimization problem where the only difference that we're going to have is, instead of optimizing our simulator, we're going to optimize F hat, which is this surrogate. And what we're going to do is we're going to choose this surrogate to be a neural network that approximates the behavior of the simulator, conditioned on a set of parameters. And so what this means is we can now apply gradient-based optimization to this differentiable neural network and then take those parameters that we learn and then put them back into our original non-differentiable, highly parameterized simulator. Now for the learning problem itself, so this is the surrogate learning problem. And just to break this apart, we're trying to find f prime or f hat, what is the best half that we find? Well, it's one that minimizes the discrepancy between this function that we're learning, and our original simulator. And based on our previous results, what we are fortunately able then to do is actually use a variant of Ithmol to then learn a surrogate for the simulator itself. Ithmol did a good job actually learning core physical measurements and the physical behavior, and we've actually been able to configure it also to learn this simulated behavior as well. Now, just pictorially, what does this mean? So if you were to plot these, let's say the sensitivity of LOVMCA's prediction is a function of changing one of these parameters. This is dispatch width, is the parameter we're changing. What you can see is it has this different response, and that's that blue dashed line. And what our trained surrogate does, what it does is ends up interpreting this line. So via this interpolation, we can get precise behavioral characterization, but again, this is now going to be smooth, and so it's something that we can actually optimize. Now for the results, so at the end of the day here, it works quite well. From scratch, we're actually able to learn 11,000 parameters that are better than the expert tune parameters. And this is all vastly better than OpenTuner, which is again, a fairly sophisticated search-based technique. And so here, this was a success for us. And if we go back to our running example, DiffTune, what it does is it gets this result, the parameters that we learn. We actually predict 27 for this example versus Ithmol's 26.8. And as well, we get a nice interpretable trace through this entire simulator for someone who wants to consume that trace and understand why this prediction is as it is. So to wrap up there, this work that we've been doing here is just a core part of this larger challenge. So learning performance models, but there's just a broader challenge here of thinking about learning behavioral models and also learning how you actually translate these programs themselves down to the wide variety of different hardware systems that we may see in practice. And so I didn't talk about it here, but we do have some work as well as thinking about the compilation problem and how we can turn the classic compilation problems that we have into learning problems where we can apply a wide variety of reinforcement learning-based techniques. All right. Now for future directions, I'm not going to delve these into too much detail, but there are a lot of shared future directions with other work that's been going on and other thrusts inside that expedition. So thinking about data generation, how do I actually manipulate our process to uncover underexplored regions of the data space? Or how do I do constrained optimization? As we're doing this surrogate optimization, what we'd like to be able to do is actually account for parameter programmer specified constraints and invariants that need to be true among parameters for them to be valid. And so these are active directions that we're pursuing. I think they'll also have great synergy with some of the other thrusts that we have going on. Right. And so to wrap up, talk mostly about the systems work here. There's a whole set of also semantic work that we think about because again, these are very different computations that we're thinking about where things like differentiable languages are really new in some sense and that we haven't fully explored all what it means for a program to be differentiable, given that the various types of differentiability that are actually available to us. And so to wrap up, this landscape of hardware systems is changing. Heterogeneity and statistical computing seem to be coming, and there's something that we have to do. So we hope some of the techniques that we're going to explore in this expedition will help us tackle these emerging challenges that are coming up. So that's it. Happy to take any questions.
Okay, fantastic. Can you see my screen? Okay, fantastic. Hi, everybody. I am going to tell you today a little bit about some of the things that we have planned in the cognitive science thrust of this expedition. And of course, Josh would have done a much better job than what I'm about to do here. But I see that Noah is in the audience and so is Zena. And I'm hoping that as CogSci experts, they'll be able to field some of the trickier questions that I may not be able to answer. Okay, so first of all, our highest level objective in this thrust is to take some of these tools of neurosymbolic learning that we are going to develop in this project and apply them to understanding the cognitive process itself, understanding the mind. And so when we think about how the mind picks up new concepts, new languages, new social rules, how the physical world works, rules of mathematics, programming, all of these skills, there is a computational process going on there. And what we are trying to do over here is to capture that computational process in code. Now, when one thinks about somebody who learns, the immediate thought is that of a child. And there is a longstanding hypothesis in cognitive science that the child is a scientist. When you are thinking about childhood learning, it's very much like the scientific process because children go and define, intuitive concepts about the world and then go and test these concepts. And then they sometimes figure out that they need to go in and try the same thing that they did, maybe with a little variation. And you can think of that as the child seeking out data that distinguish hypothesis and isolating variables and testing causal hypothesis and so on. So just to give an example from my own life, I have this adorable 15-month-old, Atish. Yesterday, he got his finger pinched in a cupboard. And first he yelled, and then after he was calmed down, he just went back to doing the same thing, but with a little bit more force. And of course, he yelled again, and you can imagine how it was for the parents. But the point is that this is, an n=1 data point for this hypothesis of the child as a scientist. Now, the way this relates to the current project is that some folks, such as Noah and Josh and Zena and other folks in their team, they have been for some time advocating the idea of the child as not only a scientist, but a computer scientist. And so what this means is that these concepts that children hold, these concepts are very naturally represented as programs. So let's think about something as basic as counting. You can think of the concept of counting as a program, as a computation in a number of different ways. So one way to think of it is that given a number n and a set x, decide if x has n elements. But there could be other programmatic ways of representing this too. Maybe you're given a set x and you have objects of different types, and you are thinking about the concept of counting as this function which returns the number of objects of type t in the set x. Or alternatively, you could also think of a function where you're given a number n and you're just returning a set of n elements. And these three are by no means the only ones. You could imagine adding more functions of this sort. But the point is that these concepts are programs, and so the process of acquiring these concepts through a series of experiences, that you can imagine naturally as a form of program synthesis. So you could imagine the child that's just starting out in the world as having a prior over these programs, and these programs represent causal models of the world. They capture, what happens when you stick your finger into a cupboard and then you shut the cupboard door. You have this causality embedded there. But they're also compositional because presumably when you have one piece of knowledge, you have another piece of knowledge, you are able to put them together into new concepts. This is something that we do all the time. And they're probably also probabilistic in the sense that they're able to represent uncertainty about the world. So these are the kinds of programs that we have. And when you're starting out as a child, you have this prior over programs. Now, as new experiences take place, you are updating this prior. And then you're also constructing, new programs by using something like Bayes' rule, but also through composition of these simpler programs. So let's try to make this somewhat concrete. Let's think about, again, this problem of counting, and let's think about the process of learning to count. Now, here is what is known from work by Josh and Noah with Steve Piantadosi from about 8 years back. So what is known is that when children first learn to count, they first learn a list of counting words without knowing any sort of meaning. They just know that you have words such as 1, 2, 3, 4, and so on, up to some length. And then they pick up the ability to count subsets up to size 1, and then 2, and then 3, and then very rarely 4. 5 plus is never, so far as I know, it's never been seen. This goes on for a little while, but then around age 3.5, they suddenly learn the principle of counting. So the principle of counting is something like this. As you are going right on that list of words that you have, so let's say that you have 1, from 1 you go to 2, then 2 you go to 3, from 3 you go to 4. As you go move one step right, then there is an extra element in the set being counted, right? This is something that's completely obvious to us as adults, but this is not something that is obvious to toddlers. And this is something that they only figure out around age 3.5. And so this learning process, for which there is evidence that goes back to actually before this paper, but this paper was able to give this computational model which explained how this process works. And so here's what that explanation looks like. So we are going to, again, think of these concepts of counting as programs. So when you are one node, that is, you know only to count up to subsets of size 1, you can be imagined to have a program like this in your mind. So this is written in the lambda calculus. So what this is saying is that if you're given a set, if the set is singleton, you say there's 1. Otherwise, you just don't know. It's undefined. 2nor is going to say, and by the way, the task over here is you are given a set, you are deciding, right? How many objects are there? Okay, so now for 2nor, it's that you know 1 and 2, but you don't know anything beyond that. For 3nor, it's that you know up to 1 to 3, and you don't know anything beyond that. But then what explains this ability to this abstract ability of that says that if you move right by 1 step in the word list, then there is an extra element in the set being counted. And so a natural way to think about this is recursion. And this was their hypothesis, and their model was able to actually explain the data that was there using this kind of a model. So when the child reaches this age 3.5 milestone, they are figuring out recursion. So now, okay, that's fine. So these are the kinds of programs that are there, but how are we modeling actually the learning process? So they viewed it in terms of Bayesian program learning. And so the context here is that you have a set of types of objects, such as cats and dogs. And then you are experiencing a set of contexts. And in each context, you are seeing a bunch of typed objects. So for example, in the first context over here under this, in this set C, you're seeing 2 dogs, a cat, and a horse. And then when you're seeing these contexts, you're also getting words associated with it. So for example, when a child sees a scene with 2 cats, maybe they hear the words 2 cats, right? And so there is an association that is formed. And so now what we want to do is to learn this distribution over programs P of L given W, T, C. That is the set of counting words is given, the list of counting words is given, the set of categories is given, the set of context is given. And now you are trying to infer this distribution, P of L given WTC. And you can imagine using Bayes' rule to basically invert this distribution. And then you get something like this equation over here. Now, one question is that, what is this prior that you're using, and how do you get that model of W given TCL? There were assumptions made about this in their paper. For example, the prior was supposed to prefer simpler programs over complex ones. But the point is that they were able to instantiate these component distributions in a way as to explain the observed transitions in the counting knowledge. And the specific algorithm that they used was Markov chain Monte Carlo. But as I'm going to say in just a little bit, one of our objectives in this project will be to bring in more sophisticated algorithms that are able to scale better to this sort of domain. Okay, so I'm just going to talk about one more setting over here where this sort of concept learning makes a lot of sense. If you think of how people learn visual concepts from just a few examples, this can arise in the setting of classification. So that is this figure 1 over here. You are given all of these different kinds of vehicles, and you are trying to classify them as something similar to what you have at the top in the red box. But you could also have other things such as generating new examples, parsing a complex object into parts, generating new concepts, and so on and so forth. So a paper from 2015 by Josh and Brendan Lake and others, this used a program learning model, a Bayesian program learning model, to explain this sort of visual concept learning. And what was interesting is that this model, which was a generative model over programs, and the programs were fairly simple, though compositional, they were able to outperform deep learning, at least as deep learning was at that point, on one-shot classification. So where do we go from here? This is all stuff from a few years back. The challenge that we have right now is that these underlying questions have not gone away at all. In fact, even counting, as I will show in just one slide, still remains an unresolved question. And there are, of course, so many other places where human cognition just performs in a way that is amazing and that cannot really be emulated by any machine that exists today. So we need to keep trying, though. So one way in which we can move forward using the tools that get developed in this project, that's to use richer models and learning algorithms. So specifically, you can imagine more sophisticated probabilistic programs, more sophisticated priors and generative models. One thing that is especially important is combination of symbolic and sub-symbolic modules. So the kind of program that I've showed so far, these are fully symbolic, but you could imagine models where you have symbolic pieces for the higher level reasoning parts, but then you also have modules that are neural networks that capture maybe representations of the world, maybe learned through self-supervised learning or something like that. And then, of course, there is the question of how do you do inference. The way they did things in those earlier papers, that scales up to a point, but presumably with our learning accelerated and solver-aided program synthesis techniques, we'd be able to learn much more complex models and thereby explain much more complex phenomena. And this can also lead to new experiments. For instance, we can try to devise new experiments that classify skills as being hard to learn or easy to learn. We can experiment if we can accelerate children's learning with a suitable curriculum, and you can imagine all of this has immediate applications in the context of education. So I'll just say that I said just a few seconds ago that even counting is not fully explained. Here are just a couple of examples. It seems like children who have mastered counting partially, they do not understand set size. And some of them do, some of them don't. And presumably more complicated models would be helpful in explaining this kind of phenomenon. Also, there are results that show that there are differences between industrialized societies, children raised in industrialized societies, and children raised in farming foraging groups. This is presumably dependent on complex environmental phenomena, which were not modeled by the existing models, but these are things that we could imagine modeling using our more powerful set of tools. So there are other contexts where we are looking into these sorts of questions. Specifically, some of us are looking into the so-called abstraction and reasoning corpus, which is a data set that's been, or a problem that has been defined to capture sort of the essence of intelligence. So here you have IQ test type questions. So let's say that you're given a few of these examples of patterns being mapped to other patterns. Now you are asked to fill up that question mark. This is something that humans do all the time from a very small number of examples, but this is very difficult for automated machine learning algorithms. But and presumably solving this kind of task would require us to get into, do sophisticated meta learning or develop other kinds of techniques that that are just not there yet. And that's one thing that we hope to do here. And finally, some folks in Josh's team, and I believe Zena and Ria are leading the development of this environment. They have developed this very interesting environment which models active causal discovery. So you're given a scene, and then you're able to click in various places. You're able to probe this scene, and then that's an action that leads to new things happening. So there is an environment that is getting updated as a result of your actions. And so humans are able to figure out, of course, cause and effect from this kind of exploratory play. But can we explain how all of this stuff happens using a computer program, using machine learning, neurosymbolic machine learning? That's one of our objectives. And as part of this, Zena and Ria and Josh and others they're in the process of releasing this corpus. It's causal inductive reasoning corpus, which has data about how humans actually explore that environment that we described in the previous slide. And the great thing here is that by looking at how humans actually come up with new exploration strategies, that is something that we can learn from when we are trying to model this sort of exploratory exploration in an unknown environment. And so I'll end with this slide, which captures, in my opinion, the essence of what all is going on here. Deep learning has, of course, been an amazing engineering achievement, but there is also a natural connection between deep learning and computational neuroscience, in the sense that you can think of neural nets as models of the brain. And when you are learning, when you're coming up with new learning algorithms, you are kind of mimicking what the human brain does. And so the analog is that cognitive science operates at a higher level of abstraction in the realm of concepts, higher level concepts and reasoning. And program synthesis can really be the analog of deep learning for this level of abstraction. And just as insights from neuroscience led to engineering achievements in deep learning and vice versa, we can imagine a two-way arrow going between program synthesis and cognitive science. And for this reason, I'm extremely excited about this thrust of our project. Thank you very much. So I won't be able to attend the panel. So maybe if there are any questions, we can just take them quickly. Of course, Noah is going to be there, and Zena is going to be around too, I believe.
Or I mean, I can give a take. Noah, if you want to start.
Sure, no problem. Go ahead.
Okay. So clearly, in behavioral science, it is not necessary to develop a theory of mind. What is it that people are thinking? How do they discover and learn about their environment? Sometimes it is. So, for example, if you want to study how mice learn to navigate a maze, there's an aspect of cognitive science there. But in general, it's more about sort of being able to sort of efficiently taxonomize, dichotomize, categorize, and analyze large amounts of behavior data in the service of some other analysis tasks. So in the context of my collaborators, they want to study how hyperactivating or suppressing activity in different regions of the brain leads to different behavioral phenotypes being expressed, which is different than what is the cognition that's happening. That's my take.
Yeah, I mean, I think that's true. It's actually really interesting because I think the terminology we're using is confusing. So cognitive science is a behavioral science. Like behavioral sciences is all of the sciences that involve behavior. I think what we're actually talking about is behaviorist models versus cognitivist models in the kind of classic Chomsky versus Skinner debate sense. So behaviorist models attempt to build models of data which is behavior. And it's not important that they're making any claims about representation or reasoning within the minds that whose behavior they're modeling. Cognitive models, on the other hand, are kind of critically, about representation and processing. And so there, the data might be the same. It might still also be behavioral data. But when you make a model, you're making a claim about things like knowledge and goals and how, inferences and how inferences proceed. So very practically speaking, I think the technical difference that ends up happening a lot is that when you're using programs, in particular neurosymbolic things, models of behavior, behaviorist models, are extremely happy to use a neurosymbolic program as a model of the input-output behavior, right? Like input is perception, output is motor actions. Cognitive models much more often use the neurosymbolic model as a model of knowledge. So basically something like this generative model that I am hypothesizing is inside the head of this person. And then we assume that the person then uses that by an inference, right? And so this is like, often when I teach this in my grad level class, I talk about Bayes in the head versus Bayes in the notebook. So Bayes in the notebook is using Bayesian methods to do data science, maybe about behavioral data, and Bayes in the head is using Bayesian models to model the processes that people are doing when they're thinking about the world. And it sounds like, oh, those are almost the same thing, but it's actually kind of radically different in terms of the formal methods and technology and like what you have to do. So sorry, that was a long answer, but that's my take.
So, I mean, it's, oh, Can you hear me? Froze there for a second. Yeah, so that's an interesting question. So I think we pursued a bit of this when you think about this latest work we have, where what we have is a fairly detailed microarchitecture simulation, and with good probability, we could say that there's some class of processors that model that fairly closely. Right. So we know that these are, hand designed artifacts given by a set of that are developed via a set of, let's say, design practices and conventions over the years that are largely consistent with the model that we can put forth. Right. And then use to guide learning. So I'm certainly in no way an expert in cognitive science. But I would hypothesize that we perhaps don't enjoy that same type of assurance in the validity of our models, though perhaps they've been validated by data, and we really don't quite know, provably know the practices by which people think and model things, and therefore those themselves perhaps more susceptible to the models themselves being invalid or misspecified in some way. Perhaps I'll throw that back to someone who knows more about that side than me.
I mean, that's definitely true. It's also kind of striking how much easier it is to do an experiment on a microprocessor, right? Like, oh man, we got 100 people to respond to our experiment, yay! And how many runs of things did you use for those models, Michael? It's amazing.
Millions. No, so that is also true. Data is free for some definition, at least in the limited context that we're looking. Certainly for larger systems, if you're trying to model a system that's running for multiple days, we're just not going to have the same flexibility. But at the level of modeling that we're doing, these are things that run on the order of microseconds or seconds at most, and so we can wildly collect data to develop those small scale models. Right? So that is another difference. And so I think it does actually influence some of the directions that we think about for the future work as well, where thinking about generative models for generating more data, we can much more actively consider sampling the real machine to think about what we're going to sample, and perhaps less so thinking about traditional active learning type techniques where we are very concerned about the cost of modeling that we're going to have, or cost of data gathering that we're going to have. Yeah, no, so I think that's absolutely true. The emergent behavior part that you talked about. Essentially, it's very hard to model, the behavior of composites, right? When I've composed, a larger system from individual components that maybe I have specified quite well, mostly well, but it's that part that you didn't quite understand, with 100% detail when composed with other components that you don't understand to 100% detail that start to lead to this type of emergent behavior that can be very difficult to model. So I do have actually a postdoc who's starting in January who's done much more of the system level modeling, thinking about learning and inferring causal models for these types of systems. So I do look forward to trying to step up another level and figure out, how can we now generate, likely more reasonably we'll have to generate programs versus working with discretely described or pre-described simulations that we have available to us.
Sure, I can maybe comment on that. I just want to echo maybe some of the stuff that Swarat talked about yesterday, since he and I collaborated on some of those projects. I think programs are, generally speaking, I think it's fair to say that they're a lot more sample efficient than neuro learning. So, deep learning is very data hungry, and program learning, I think by comparison, certainly is much more data efficient. And so that has a lot of implications in terms of, how you sort of blend, when you think about blending the two, in terms of, where you lie on the data efficiency spectrum, how do you transition from one to the other? And so that's one aspect. The second aspect is in the optimization. So continuous optimization is, I think it's fair to say, at least today, much more tractable than discrete optimization. And so, backprop gradient descent, in some sense is king in terms of optimization. And so, Swarat talked about using neural relaxations as a way to get speeded up an optimization over discrete search as an admissible heuristic, for instance. And so I think those two aspects suggest, going back to your question, Armando, that, there are many applications where you want to start off with an initial program, possibly handcrafted. Certainly in the applications I work on, that's sort of the starting point. And then learn a neural relaxation around it and then iterate. And that seems to be, in broad strokes, the optimization philosophy, and that's coupled with the domain knowledge integration philosophy that works really well for many of the applications that I work on.
I guess I can make a comment from the cognitive science point of view, which is, in terms of techniques, I think what Yisong said is right. And, I thought Osbert's examples of where the symbolic structure allows you to have an amount of abstraction, which is, useful, was quite compelling. For cognitive science, I think we should treat it much more as an open hypothesis. So there are cases where we know there's something discrete that comes out of humans, like language, the things I'm saying are discrete words. And so it's very much if we want to model human cognition, there's somewhere where there's going to be a discrete interface, language. How far we want to push that discreteness back is, I think, a totally open cognitive modeling question, right? It's it could be that we do something like BERT and GPT, where the discrete stuff really happens only at the very end, right? Like there's a final softmax embedding thing, or initial, depending on which direction you're going, and that's it. Seems to work kind of well. It's interesting, we don't know actually at this point how far that can go. Or you can do the opposite, right? And you can say, well, let's build the discrete structure of concepts and their relations and their causal and inferential roles into the latent representation. And then it's really easy, words kind of hook into that existing discrete structure. That's the other end of the spectrum. And I think Josh and I pushed that, discrete concepts, probabilistic language of thought thing a lot for a long time. I sort of still think that might be right, but I think it's, much more an open empirical question, which, where on that spectrum do we actually end up when we're trying to model data?
No, I'm basically in the same camp as by saying I don't quite know, and perhaps we're actually at least the work that we're doing right now is at a different point in terms of the size of the programs. The programs that we have are rather large. I think comparatively to much of what I see normally in the synthesis literature, and so just even the idea of doing verification on these programs at scale is a bit daunting. So it'll be interesting. So I do hope that we see some opportunity to be able to leverage this type of neural continuous relaxation, but also at the same time, these programs are detailed enough that I've so far actually been surprised that they've been able to capture some of the subtleties of the behavior that we see. So I think this is sort of where we're sitting, where both approaches look a little dicey, but we're trying to use both. In some future work, we're definitely thinking about symbolic ways of doing data generation, where we really would like to be able to generate new basic blocks that get more coverage throughout the models that we have, as guided by, for example, Fisher information statistics that tell us where we've are relatively insensitive in the parameters that we characterize so far in the model. Right, so these are sort of course concepts that we have, and we're trying to blend the both and see what possibly falls over.
I have a question for Michael, actually, which is, so far, like, you characterized what you're doing as, take a chip which somebody made to do the right thing and then characterize kind of behaviors like time and stuff. At what point do you get to switch and say, okay, now let's start making chips that we don't really know how they work inside? They're just like, there's some broken bits and some complicated bits, but as long as we can then characterize them, we can use them.
Yeah, so that's, if you talk to the architects, that's what they'll say the dream is, where you can use these types of neural models to do design exploration, right? Where if you have this parameterized simulator, for some definition, they can take any setting of those parameters and say, I can build hardware that matches the behaviors that you'll see out of those parameters. So then what you want to do is take a program, you want to take data, and then try to find, how could I make this data, where the data now programs, go as fast as possible? What are those settings of the parameters? Right? And if I do that, then I can tape out hardware. Right? And so I do think you will see more of that come out. And so people have certainly seen some of this work that we've done and asked this same question. Can I use this now to just automatically do design exploration? So yeah, it's a very good point, right? And I'd say some of the detail and magic there is getting back down to the fidelity of the simulation, right? It is this black magic of writing a system simulator that really precisely corresponds in its parameters to the hardware that you have at hand. But if you can do that well, then yes, I think there's some opportunity to do that.
Cool.
Yeah, no, that's exactly right. Your model needs to map to hardware, approximately map to hardware that you can build, right? So those parameters need to be interpretable in some way. A big neural network isn't going to help you out too much.
One of the things, I actually have maybe it's not, it's sort of a half comment, half question back to your earlier question, Armando, about where you draw the line between neural and symbolic. So one of the things that I do a lot is I collaborate with scientists who wish to derive insight from observational data, ideally for the purposes of designing a new experiment. And so for them, the symbolic aspect is what is interpretable to them. Mm-hmm. So just to give like a super simple example, a lot of times what happens in the past is they train a recurrent neural net, autoencoder type, whatever, transformer, whatever this flavor of the month is, on this behavioral tracking data. Trying to be a little bit careful with my terminology after I've been educated by Noah. And then they, let's say they take an embedding from that and they do t-SNE on a two-dimensional t-SNE plot, and they look at clusters, and like that is literally like the state of the art in terms of data analysis for this large amounts of behavioral tracking data. And so, when you say, where do we draw the line between neural and symbolic, that's a question I struggle with in the context of that type of question. How do we make these things more amenable to discovery for these scientists? And, if I might just draw small parallel. It's like, what is useful for the cognition of the scientist in terms of understanding what's going on? Because, you know, in some sense, humans, when they try to understand the world, they have to discretize the world to some extent. So I can comment on interpretability with respect to experiment design. So, just concretely, and I'm going to butcher this a little bit because I'm not a behavioral neuroscientist. My collaborators, they try to correlate activity in the brain at the neuronal level to behaviors, like aggression, right? And there are obvious applications to mental health and other things in the human brain, but at this fundamental level, that's what they're doing. And now we can ask the question, okay, suppose we came up with a hypothesis that this part of the brain is associated with aggression. If I forcefully suppress activity in this part of the brain, which you can do for, in mice with various equipment, neuroengineering equipment, does that lead to a difference in behavior? And you could run that experiment. Of course, that experiment is very expensive to run. You have to do a surgical operation and all that stuff. But in the end of the day, that those are the things that lead to significant advances in this area of neuroscience. So you have to the neuroscientist has to have confidence that whatever the model, the data analysis is giving you, is worth following up with that level of investment in an experiment.
I just wanted to say on interpretability, kind of follow up, like I agree with what Yusung was saying, and I think that's a case study where it's kind of clear what's wanted. In general, I think interpretability is kind of an uninterpretable mess. Mm-hmm. It's like I think fundamentally, like what people want is a feeling of explanation, like, oh, I get it. Unfortunately, psychologists have argued for quite a while that we're subject to these what's called the illusion of explanatory depth, right? Like we see a thing that's kind of truthy, and we're like, yeah, I get it now. I can interpret this now, and that might or might not actually like give us any real explanatory power or predictive power or ability to do anything. So, I guess I love the idea that programs are powerful because they can help you think, and I hate the idea that merely by having something that's a program, you gain interpretability. Actually, as I'm saying this, basically, yeah, it should be totally like, kind of task and use oriented.
Yeah, that's been my experience as well. Interpretability in a vacuum is just really hard to frame in a productive way. I think there's two types of trust. There's trust in the sense of I have a sense of what the system is doing, so I can build a model of how the system operates, so that if I were to ask different queries or query the system in different ways, it would give me answers that can help me build an understanding of the phenomenon I'm trying to model. And then there's formal trust, like verification style, where someone gives you a certificate that the system will behave according to these specifications under these input conditions. And so I think those are two very different notions of trust. Both of them can be facilitated with neurosymbolic or learning as opposed to just purely neural learning. In the latter case, I do some work with roboticists and control theorists, and formal trust is absolutely crucial to getting them on board with deploying neural or neurosymbolic methods onto in safety critical autonomous systems.
Okay, thanks. So just a general kind of question on the cognitive science thrust. I guess there's a lot of argument that program synthesis or deep learning or neural networks are good models for human learning. And if we believe this, then to what extent do we think that empirically evaluating these kinds of algorithms can help us understand human learning? And I guess also along with that, has there been any work in this direction in CogSci?
By empirically evaluating, do you mean empirically evaluating with human experiments?
Well, I mean, thinking about it in isolation, like, if you believe this is a model for human learning, how much, has there been any success in like trying to evaluate the model, like a program synthesizer in isolation to reason about how humans might learn? Is that something with Loop is possible? Right. Yeah, exactly. So yeah, I guess eventually you might tie it back to learning and, tie it back to experiments, but kind of using these to formulate hypotheses. Are there any examples of that?
Well, it depends whether you're taking these systems as the hypothesis about human learning, or you're trying to use these systems to build models which are a hypothesis about human learning. It sounds like you mean the latter, is that right?
I guess not trying to use these. Yeah, I guess so. So I guess if you think of these like as resembling human learning, it seems like they should be useful for formulating hypotheses about how humans learn, right? And I'm wondering whether that's has been, or you think it would be a fruitful research direction.
So from the point of view of like where Josh Tenenbaum and I and some other people like Xana are coming from, I think that's where we started, right? Like there's a extremely long history of experiments on human learning and especially human category learning, right? Going back to like Jerome Bruner, and that's a setting. It's arguably it's much more local than real learning, like what kids do. But it's a setting where you can get a lot of laboratory data about how humans will learn a new category. And like, I, for instance, got into the whole thing about programs and probabilistic programs by first modeling human concept learning as Bayesian induction for propositional logic formula. And that turns out to be really, really, really good at modeling human behavioral data about, like, you show people some examples and then you ask them to generalize to new objects, whether it's true or false. They give you data and you can model that data pretty well. It's not unique. There's other ways to also model that data. So yeah, I would say for that kind of thing, the hope is exactly that, like, great, as we get better techniques that can do program induction from more data and more complex programs, then they would be hypotheses about how humans learn concepts, which we could test. It gets hard. It gets very hard very quickly to test some of these things as the kind of conceptual knowledge gets complicated. But tell me if that wasn't actually the question.
Yeah, I think that gets at the question, but yeah, thank you.
I don't know, Xana, do you have a different take on that?
No, I think that's how I think I follow that way of thinking. I guess I would only add that um, it's hard to evaluate many of these things, both experimentally and also just technically. So a lot of these, a lot of the kind of the terms that arise when you start trying to do kind of Bayesian probabilistic program learning are all intractable. So uh, I think it's even coming up with good evaluation metrics is a difficult problem in its own right, and I think that's something that we're going to have to tackle with in this program.
Yeah. Thank you for organizing, Armando.
Thanks for organizing, Armando.
Yeah.
Yeah.
Right.
Right.